Ça marche.
So,
Ok, c'est parti.
Hello everybody and welcome back to this OceaniX webinar series. Today we are extremely happy to welcome Nicolas Thome, who is professor at le CNAM. So Nicolas is going to talk to us today about hybrid dynamical systems, so augmenting physics with machine learning. So as usual, we'll have around 45 minutes for presentations, and we'll get some times to ask questions. As usual, you can also post your questions in the chat, and I will read them to Nicolas after the presentations. So thanks again, Nicolas, for giving your this presentation today, and you can start.
Okay, so thank you, Said, for the introduction. So yes, I am professor at CNAM Paris in the computer science lab and Cedric lab and the machine learning team. So I'm very glad to talk about hybrid dynamical system today, and especially how to augment simplified physical model with machine learning. So okay. The outline of the presentation is pretty standard. So first, I will draw the context of this work and what are the main challenges and the main opportunities to combine machine learning and AI in general with physics and physics prior. And then I will detail two of my recent contributions on that topic about using physically constrained model for deep video prediction, unsupervised video prediction, and a specific focus on how to combine and to make physics model and machine learning cooperate with the affinity framework. So the general context of this talk is about spatial temporal forecasting. So the overall objective is to perform future prediction of a time series with potential spatial correlation. So there are various tasks and applications for that. So for example, in the time series forecasting for finance, for particle physics, and when you deal with spatial information in images and video for weather and climate science, also for healthcare and for physics or robotics in general. And of course, several important applications in general for the society, such as anticipating flood or hurricane and so on, or other extreme event that can occur and for which the proper and accurate modeling of this phenomenon could be helpful. Okay, and from the machine learning perspective, of course, we have a super abundance of data in this context and in this task, which can come from this time series sensor when you have temporal and monodimensional problems, or when you have images such as satellite images or fisheye images. I will come back to this point, which was closely related to one of my applicative problem. And of course, again, spatial temporal data when you want to perform several tasks such as weather forecast and so on. And here, of course, the main observation is that we need to develop artificial intelligence tools to process this data, which we will not be able, of course, to handle and to process manually due to the huge quantity of data that we have to deal with. Okay, and in terms of state-of-the-art method for this problem, so performing, trying to extrapolate and to predict the future evolution of a given time series, of a given spatial temporal time series, you have at one extreme you have model-based approaches, and for example, if we are dealing with a dynamical phenomenon which can be described by partial differential equation or ordinary differential equation. So this approach relies on a deep understanding of the underlying phenomena, which is described, for example, by this equation. And for example, this is what is shown on here on the right hand side of the spectrum. For example, when you deal with simple Newtonian physics law, which are pretty well described by by ODE equation or computational fluid dynamics, or in general in quantum physics. So in this context, you can have a pretty accurate model for the description of this phenomenon. And when you move to more generalized data, for example, on the left side here of this figure, when you deal, for example, with generic video prediction, just to perform to describe the evolution of a video, then state-of-the-art approaches nowadays essentially relies on machine learning models, which are more agnostic, because it's very difficult to have an accurate model for describing the evolution of the state dynamics in this case. And in between these two extremes, there has been an increased interest in the last few years to develop hybrid model-based and machine learning models. So this has been a hot topic in the current era of deep learning, but of course it's also a very old framework or pipeline, for example, which come based to seminal work of data assimilation method, which certainly was the oldest method for combining model-based and machine learning approaches. Okay. And a representative approach of this recent trend combining machine learning and model-based approach is certainly neural ODE. So the idea behind this neural ODE model is to parameterize the state derivative of a given variable h, and to try to train this derivative f, which depends on the state h at time t and some parameter theta that we want to learn. And it can be seen as a generalization of a residual model, which can be seen here on the left-hand side of this figure, where you, in a residual network, you describe the latent vector at times t plus 1 as a function of the latent vector at times t plus some function, some residual connection f. And here, this neural ODE network can be seen as a continuous limit case of this model, where the time step goes to 0. And then, really, in these approaches, the idea is to be able to train from data this derivative by model and parameterized by this parameter theta. And there are some nice property when you want to train that using backprop and neural network, because the gradient and the backward parts can be computing efficiently with the joint method. But on the other hand, one of the main limitation for our purpose of this kind of model is that still the dynamics that we are trying to model is still purely data driven, meaning that the function f that we train to learn is optimized only based on a set of label or observed data. There is no explicit physical knowledge in this kind of models. Okay, and from an applicative point of view, one of the important application which have been interesting me in the context of the PhD of one of my former students, Vincent Le Guen, who just defended a few months ago, and it was a PhD with EDF, and the main goal of this PhD was to perform short-term solar energy forecasting, just basically to predict how the radiance, the irradiance will evolve in the next, let's say, 20 minutes, something like that. This is this kind of context for short-term forecasting and prediction. And at EDF, they want to perform this prediction based on fisheye images. That is what is shown here on the right-hand side of this slide. So we want to equip to have some equipment based on fisheye images, and the idea is to use this fisheye images in place of the standard pyranometer, that are shown here on the left-hand side, because they are much cheaper. And so one of the main goals is to be really able to replace this parameter. And at EDF, so they collect a massive amount of label data where you have the fisheye images plus the ground truth annotation from the for irradiance, which constitute a data set of more of 7 million images that have been collected in the last decade by EDF. And what we observe in this PhD, that if we want to perform the instantaneous solar prediction forecasts, so it's let's say a perception task, and it works pretty well because we had a very large data sets. So it was pretty easy to replace this parameter by fisheye images for this instantaneous perception task. But on the other hand, when we move to this short-time future irradiance prediction problem, it was much more challenging. And just to illustrate that, so what we show here in this curve is on black is the ground truth irradiance, the actual ground truth irradiance from a given actual measurement, which is shown in black here, and you have from A to A prime a large increase in irradiance, and from B to B prime a large drop. And what we observe by using several state-of-the-art at this time deep learning models, so convolutional neural networks, recurrent model based on LSTM or 3D convolution, or a combination of both used with convolutional LSTM, was that none of these state-of-the-art model perform very well as this task. And even surprisingly, a very naive model, which is shown in gray here, which is a persistence model, which simply assume that the solar irradiance in the future will be the same as it is now, is a strong baseline compared to this deep learning model. And it really shows that to perform well on this extrapolation task, we need to have smarter model and to somehow include prior knowledge on the dynamics to perform well at this task. And this is the main problem and the main research direction which have been interesting me in the last few years, is how to properly exploit prior knowledge on the dynamics to improve such machine learning and especially deep learning forecasting models. And I have been contributing at this problem at two levels. So the first solution to include prior information in machine learning and deep learning model is to add some constraints during training, and when you have some physical constraint during your training, and this constraint can be seen as a regularization term during training, which is the standard way this is addressed by physics informed neural networks of these TINS models. And in the PhD of Vincent Le Guen, we have been contributing at this level by proposing several loss functions that include or incorporate our prior knowledge on this type. So, for example, loss function including prior about the shape or the temporal delay of a drop in this time series. So I won't talk about that today, but it was one of also one of the important axes we have been interested in. And the other solution is to explicitly incorporate these constraints into the deep network architectures. And here, just to give a few examples, I describe here two examples of approaches which are representative of this problem. So the first one is this advection diffusion flow model, which has been proposed by de Besnac and his colleagues in 2018. And it based on explicitly including a prior knowledge from an advection diffusion equation. So this equation, and we assume that our problem follows this PDE shown here, But there are some unknown in the problem. And here there are two main unknown, which are the diffusion coefficient D and the vector field W, which can be interpreted as an optical flow field. And here, the idea in this work is really to combine this explicit advection diffusion equation with a deep neural network, which is devoted to estimate from data this W field. And so we have this equation and we estimate this parameter, this W parameter from data. And this is what we call physical parameter identification, because we know the equation, but we don't know some characteristic parameter from these equations. And another popular model in this field is the Pdenet model. So the Pdenet model is based on linear PDE shown here. So you have the temporal evolution of this variable u, which is described as a function of spatial derivative up to a certain order. And in this, the simplest form of this approach is to assume that that this PDE follow a linear PDE, so such that you have this temporal evolution which depends on a linear combination of the spatial derivative. And again, the main challenge here and the main objective here is to estimate the linear coefficient Caj from data, and again to perform physical parameter identification here. And to train the network and to train the parameter of this model end to end, we can simply approximate the spatial derivative with constrained convolution with an approach based on the moment to have a pretty accurate approximation of this spatial derivative. Okay. And so in this field of hybrid machine learning and model-based approach, in general, most of this model assume that you have a given description of your system that is accurate. And it is an assumption which, up to some extent, it's not fulfilled in a real-world application. In several applications, you have models which only capture a coarse approximation of the real-world phenomenon that you want to describe. And here I give some example just to justify that. So there are several sources of approximation that you can have in this problem. So let's say basically you can have two kind of approximation sources. So the first one comes directly from a modeling approximation, because in many cases we are not able to properly describe the full evolution of the state. For example, if you as an example, if you take the example of weather forecast, we are not able to write all the equation at the microscopic level. And there can also be some approximation at when you want to solve these equations. So for example, in computational fluid dynamics, in general, the Navier-Stokes equation are a pretty accurate description of the evolution of the fluid. But when you want to solve this equation numerically, then you have to rely to some approximation. And for example, it is well known that these approaches it's very challenging to make these approaches to describe properly the evolution of a fluid in a given regime, for example, to describe the turbulence. In quantum physics, also, for example, several approximations are used to solve the equation, for example, using some Born-Oppenheimer approximation from this Schrödinger equation. And so, in this work I'm going to talk about here is really to compare to this approach, which assume a complete and a full description of the system, to try to leverage some simplified physical model, which will only capture a subpart or a coarse description of the dynamic, and to try to complement them with machine learning and data-driven networks. And that's what I'm going to detail now. So with a first work with dealing with partial observability, meaning that you assume that you have a physical model, that this model does not apply directly in the input space, and to try to leverage some physical dynamics, some PDE dynamics in a learned latent space. And a second work focusing on how to properly make this machine learning and model-based approach cooperate, such that you can solve the problem and you can have some guarantees of on the decomposition. Okay, so now I will switch to this first work, which is called Pdenet for physically constrained deep video prediction. And here, the goal of this work is to solve unsupervised video prediction. So you have a given input video sequence, so a very generalist video, which, as we will see in the XP, I will present results in several different contexts. And then you want to predict the evolution of this video. And here, what we propose in this Pdenet model is to somehow disentangle the prior knowledge that we will have on the evolution of these dynamics from some complementary information which are required to perform an accurate prediction at the pixel level. So basically, this is the motivation of this approach. So here, what is shown is a standard academic dataset, which is the moving MNIST dataset. So you have this standard manuscript digit, and they follow a linear translation model. And the digit can also bounce on the walls, on the boundary of this world. And here, what we assume is that in some abstract latent space, for example, which is shown here on the left, so this abstract latent space can be, for example, regarded as a way to capture object and to perform a coarse segmentation of the object and to follow their position and their sizes. And in this latent space, we assume that we have we know the dynamics of this object in this latent space. And for example, that in this space we can follow a simple PDE, such as a linear PDE. And then when we have this model, of course, it will be a too simplified model to accurately predict the evolution of the dynamic at the pixel level. There might be two main reasons. For example, this simple linear PDE will be able to will be pretty efficient to predict the evolution from this linear motion of the digit, but it won't be able to model the bounds on the wall and all the contacts which cannot be described by such a simple linear PDE. And then we propose to augment this in the latent space, this simple dynamics, by another network, which will be a machine learning model, so a deep neural network, which is devoted to capture this extra information that is ignored in the simplified model. So it can help to represent this bounce and this nonlinear dynamics effect, but also more complex effects based on the factor that you miss with this linear PDE, such as appearance, texture, and some details on the appearance. Okay, and so more formally, so let's consider that you have as input an image sequence. So at times t, you have a given image parameterized by some spatial coordinate x. And then we encode this image into a latent space. So you have this E of ut of x, sorry, which gives you this its h vector, which will be our latent representation of our input image. And in this work, we assume that in this latent space, we can decompose the PDE dynamics as a sum of two terms. So that's what is shown here. We assume that this dynamics, this partial derivative of h over t, can be decomposed as the sum of hp as the derivative of HP over time plus HR. So HP will be the part of the dynamics which will follow some physical and some explicit physical prior. So which is this MP here shown here. So this is what is shown on the left hand side here of this model. And for solving these dynamics, we will use this explicit model, and we will use a physical model which we call the Pcell for solving this problem. And on the other end, we will have another dynamical term, which will be the residual term, the complement of this simplified model, which will be modeled by a simple or standard data-driven model. And here we relied on a convolutional LSTM model. And then once we have this assumption of this linear decomposition of these two terms, we simply sum these two derivatives to give us our estimate of the dynamics at time t+1. And then we use a decoder D to predict the subsequent image U at time t+1. Okay. And a bit more detail. So what I show here is how this Pcell, so this physical prior, is designed. So just to remind you, it's what is shown here on the left hand side of this figure. So here we introduce this Pcell, which is basically an atomic primitive, an atomic recurrent cell for building physically constrained recurrent neural network. So it is based on recurrent architecture, and importantly, it is based on the prediction correction paradigm, so which is reminiscent from all these data assimilation methods. So you have your latent vector at time t, and what does the prediction stem perform is to predict the evolution of this latent step at time t+1 using a prediction model. And here, as a prediction model, we use a simple Pdenet in the latent space, meaning that we assume in this latent space, that is shown here, that these 5 functions follow a linear PDE. So again, our main objective will be here to try to identify this linear coefficient Cij, such that we can learn this weighting coefficient from data. But apart from this weighting coefficient, we enforce explicitly this linear PDE in the latent space. And then, so this is the prediction step, and we also have a correction step where we compare the actual prediction compared to the current prediction compared to the actual observation, and we perform a correction step, which is basically an extension of Kalman filtering in this non-linear case. And here, what we propose here on the left-hand side is to learn this Kalman gain using gating mechanism. So okay, and okay, there have been recently several proposals to extend this Kalman filtering for deep neural network, and here we follow a different strategy compared to what was done in a state-of-the-art model, where they assume that you have a locally linear model. And one important feature of this prediction correction step is that by doing so, we can decouple by design prediction and correction, and it offers appealing property for being robust to missing data or to perform long-term forecasting. Because if we have unreliable data, input data, then we can only rely on the prediction term here shown on the left. And this is something that cannot be performed by standard data-driven models such as recurrent model, RNN, or LSTM. Okay, and so this we perform several experiments, so I won't I won't comment on all the results shown in this table, but we compare the performance of the model at the time of the publication compared to state-of-the-art model. And here, this first set of methods here are data-driven approaches. And we compare also our model to more specialized method that can be optimized for a specific data set. Because as you can see here, we perform experiment on 4 different set of application. So this application, which consists in predicting the evolution of the temperature at the surface of oceans, and this is for this kind of model. For example, you can have explicit or dedicated models such as the advection diffusion flow model. And we also apply this approach to much more generalist videos, such as human motion, predicting the evolution of video from human motion, moving digit, and also traffic data set and traffic video of videos of traffic. And what we can see is that our approach perform well, and this approach managed to outperform fully data-driven approach, and also in some cases some much more specialized approaches. Okay, and in this experiment also, what was pleasant to see here, what is shown here is on the x-axis for all of these 3 data sets are the different moments of our linear PD that we impose. So we have a linear PD up to which model the evolution of the dynamic as a linear coefficient of the spatial derivative up to a certain order. And what we show is the energy of each of these spatial derivatives. And what was pleasant to see, for example, on moving MNIST, is that the most dominant coefficient was this first order coefficient here, which is related to the uniform translation motion of the digit that we can have on moving MNIST. And on the other end, on other data set, for example, on this traffic, on sea surface temperature, or on human motion, you need to include energy from much higher order derivative to properly perform, to properly predict the evolution of your dynamic. Okay, so this was the first attempt to try to really include some prior knowledge. So in this form of this simplified, this simple linear PD, and to try to complement it to complement it with data-driven models. So now what I'm gonna present, and I will be more focused on how to make these 2 components optimally cooperate, such that you have a proper decomposition between them. And here, in this case, we come back to the fully observable setting, meaning that you assume that you are in a setting where you have a state variable as input, which is directly of interest for your problem. And as an example, for example, I will take as an introductive example the problem of the pendulum. So here is the ODE from a damped pendulum, where theta is, as shown here on the right-hand side, is the angle of the pendulum. And our goal is to be able to properly describe the evolution of this theta angle over time. And we assume that we have a damping factor, which is represented by this first order temporal derivative with parameter lambda. And if we want to predict the evolution of such simple model, if you use purely data-driven model, so for example, if you use state-of-the-art neural ODE model, so the model I was presenting in the introduction. So if you don't have enough data, there is a strong risk of overfitting, and that is shown on what is shown here on the left-hand side. So again, on the x-axis is represents this angle theta over time. we can see that the ground truth dynamics, which is shown in red, cannot be properly predicted by this fully data-driven model. And clearly, in this low data regime, the model overfits and then is not able to properly describe the dynamics. On the other hand, let's assume that you have a knowledge on these dynamics, but a partial knowledge or an incomplete knowledge. And in this case, for example, let's assume that you know that your pendulum follow this ODE, but you don't take into account this damping factor. So you have a pendulum equation without accounting for this damping factor. So if you do that, you obtain something like that. So something shown in the middle figure. So where we can see that we are able to represent this periodic motion of the pendulum, but by design, the model is not able to take into account and to represent this damping evolution. And there are, let's say, two main shortcomings when we use this simplified model to solve this problem. Is that, of course, it makes the forecasting error increases, as we can show. Of course, the model by design is not able to properly represent the evolution of the dynamics. But if we are interested in physical parameter identification, for example, here estimating the period of the pendulum, this simplified model leads to an increased error on this estimation of this physical quantity, and which it really comes. It's really the consequence of a biased estimate of this quantity due to an oversimplified model. So you are bad both at forecasting and at physical parameter identification. And here our idea again is to try to leverage this simplified model, so this ODE equation without the damping factor, and to use a machine learning approach or a deep neural network to try to regress and to train this missing component from data. And by doing this, as shown here on the right hand side, we are able to properly describe the evolution of the dynamics and also to perform a much more accurate estimation of the underlying physical parameters. And so this is the idea behind this work, so which is based on augmenting physical models for identifying and forecasting complex dynamics, and which is called affinity. Okay, and so here the main contribution is this work is to have a well justified way to combine these two dynamics, the dynamic coming from a coarse physical prior and the other part of the dynamic coming from a data-driven component. So more formally, let's consider that we have that we describe the evolution of a state vector x, big X of t, and we want to represent the evolution of the state vector over time. And so our goal again is to train this f function, which is a derivative of this temporal derivative of this state vector. And in our application, x over t can be a vector of d-dimensional vector, but it can also be a vector field in the different application we have been interested in. And so our assumption is that this function f, so this derivative of our state vector belong to a given norm vector space, and we assume that we have a state fp, which is included in f, which represent our simplified physical model, so which can be described by a given ODE or PDE, depending on the context. And again, we follow the same intuition as before to augment the dynamics coming from the approximate models of this fp term. And so we assume that the dynamics is simply a sum of this physical term plus this augmented term fa, where fa belongs to the full state, so to the full space, sorry, f. And here the first observation is when we simply sum up these two components, the decomposition in general is not unique. And for example, there are clearly this is clearly a nilpost problem, and there are clearly degenerate solution. For example, imagine that your solution is to put FP to 0, and then in this case all the dynamics will be modeled by this FA term, and then we come back to a purely data-driven model, which again is not what we want here. And so to have a more meaningful combination, what we propose is to enforce this sum of these two terms. So we want F, the actual dynamics, to be representing as a sum of FP plus FA, but we want to minimize the norm of FA. So the intuition behind that is really that the augmenting term that we include only capture the minimal information that cannot be modeled by the simplified model. So we want only to add the minimal and the required information to properly describe the evolution of our data. And interestingly, we can have some theoretical guarantee of the decomposition. So under some mild assumption, so assuming that our physical space FP, so the space of where we include our simplified physical model, follows some structure. So here we assume that it fulfills the property of a Chebyshev set. So Chebyshev sets in final dimensional set, they consist in a closed and a convex subset of the initial set. Then we can ensure that the decomposition in this equation exists and is unique. And basically, it is simply a generalization of a projection in linear space, which consists here on a metric, in what is so-called a metric projection of F into the FP space. Okay, and that's what is shown here as an illustration. So you have our target function F, that we want to represent, and we will decompose them as a sum of one element belonging to a subspace of FP, which will be a convex closed set in F, plus an additional term that we will train from data. Okay, so the main point here, based on this decomposition and based on the minimization of this functional norm of the augmenting term, then you can have a unique, you can have a decomposition that exists and is unique. And so now, more practically and more algorithmically, so to train the model, we assume that we have a data set of observed trajectories. So we have D, which is composed of a set of trajectories which map a given time step on 0t to our f functional, which represents the derivative of our state vector. And our objective is to fulfill this, to optimize this affinity objective function, where we want that the derivative of our state vector can be decomposed as a sum of these two terms, fp plus fa of xt, under the constraint that we seek for the decomposition of minimal augmenting norm fa. And so in practice, we use parameterized model. So we have a model, let's say, with two components: a physical component where we have theta p parameters. So in general, this component contains very few parameters. So these are the physical parameter of interest for our problem. So for example, for our pendulum, it can be the period of the pendulum. So let's say we have more than 10 parameters in general, so very few parameters. And depending on some initial condition, these parameter which parameterize the FP derivative can be used to predict the evolution of the dynamics. For example, using any solver, any ODE solvers to predict the evolution of the dynamic. And then this derivative will be combined with another branch, which will be a data-driven branch parameterized by parameter theta a here, which will be much more numerous, because this model will be in practice a deep neural network. So it's a fully parameterized model, and then we simply sum these two derivatives, predict the evolution of the dynamic, and then what we compute is the loss of our trajectories and we backpropagate this loss to optimize the parameter, to optimize jointly the parameter of the two branches, the parameter theta p and theta a. Okay, so as I say, so during training, we are, so as input, you have initial conditions, your actual parameter, and it gives you an estimation of the model trajectory. And we use a trajectory-based training to compute the loss between the predicted trajectory and the actual trajectory. And we add, we also add an adaptative constraint. We also leverage an adaptative optimization constraint solver based on a variant on Uzawa algorithm. So basically, it's a way to make the regularization term between the minimization of the norm and the trajectory loss to be adaptative over time. And that is what is shown here in this algorithm one, where you from this model you are able to compute the gradient of your parameter over time. Okay, and from this model we perform experiment on 3 classes of physical phenomenon, and so these three classes of phenomenon cover different application, but also different classes of ODE and PDE. So as I described before, we perform experiment on this dumped pendulum equation. So here this is the full equation of what we are interested in, and we use several simplification of this model based on an Hamiltonian model, which is based on energy conservation, and as I mentioned before, the ODE without this damping factor. So a pendulum equation without damping. We also consider an application for reaction diffusion, so which is here a 2D vector field. And what we show here is this reaction diffusion for the state vector, which is composed of U and V, which are shown here on the top and on the bottom of this middle figure. And we have this PDE, which is described as a diffusion coefficient with a Laplacian and a reaction term. And so again, our goal is to predict the evolution of these dynamics described by this full model using simplified physical model, here composed of the PDE without the reaction term. And finally, we address this dumped wave equation problem, which is well known in electromagnetism. So where you have this W state vector, which second derivative over time is modeled here as again with as a diffusion term with a Laplacian and a damping coefficient with damping coefficient K. And here we also use a simplified model of this PDE without damping. And so the interesting point in this free class of problem is that we can easily show in this approach that all the simplified model that we have been using, they belong to spaces, to FP species, which are closed and convex in the initial space, and then they fulfill the Chebyshev assumption of our model. So then, based on this simplified model, we can guarantee that our decomposition exists and is unique. And here, what I show here are the main results of this model. So there are several results, but the main point is that so we compare our model, which is affinity, when it's combined to several simplified models. And the main observation, the main take-home message of this result is that with affinity, we are able to improve the forecasting performance, which is measured as a log MSE as shown in this first column. So for example, when you have an incomplete physical model in this reaction diffusion problem, then you are able to significantly improve the prediction performance, and it's true for the three kind of applications, but we are also able to significantly improve the physical parameter identification. For example, here, if you look at the performance for parameter identification, we have a very large improvement from let's say about 60 to 2, about 2. And really it shows that having a more accurate model is not only helpful for forecasting, but it's also helpful for physical parameter identification. And finally, an interesting side effect of the model is that when we minimize as we are attempting at minimizing the norm of our augmented term, the actual value of this norm, of the norm of FA, it gives you an idea of the level of approximation of our simplified model. For example, the norm of FE when we have when we include the ground truth dynamic is about 0. And on the other hand, when we have a simplified model, it's much more large. Okay, and finally, some qualitative results. So here, qualitative result for this reaction diffusion on top and wave equation at the bottom. And what we show here is the results of the ground truth simulation on the right hand side. And what we can see is that with affinity, we are able to properly describe the evolution of the dynamic compared to the ground truth simulation, which is not the case with a simplified model as shown on the left. And on the bottom part, we show again the ground truth simulation for this wave equation and how this affinity framework is able to properly represent it, and which is not the case to a fully purely data-driven approach as shown with this neural ODE framework. Okay, and finally, we propose to combine this idea of minimizing the term of this augmented component in the context of unsupervised video prediction, and more precisely in the context of unsupervised video prediction for fisheye images, so related to the problem of irradiance forecasting that I mentioned in the introduction, and which was the applicative problem for the thesis of Vincent Le Guen at EDF. And here, what we can see when we include the constraints, when we include the constraints in the decomposition coming from the minimization of the residual term, is that we can improve performance compared to the Pdenet approach that I mentioned in the first part of my talk. For example, here in this problem, we were able to gain to still improve performance by this constraint, and by which ensure to have this unique decomposition. Okay, and qualitatively, that's what we show here on these results. On the first row, you have the input video sequence from these fisheye images. You have the target, the ground truth evolution of the video, and our prediction. Okay, an observation is that our prediction, in general, they remain blurry, so we don't have any constraints. We do not try to have really sharp images, but overall, the estimation was able to follow the evolution of the cloud, for example, which explain how they are able to predictly track the evolution of the irradiance over time. Okay, so as a conclusion, so what I presented here today is new hybrid model for combining machine learning, for including machine learning into model-based approach. And the main idea is to leverage approximate physical models and to improve forecasting, performance, and also physical parameter identification. What's important to notice is that it's important in this kind of framework to think on how the decomposition is performed, and it's important to add some constraint to make this decomposition meaningful. And there are certainly many important applications where this kind of approach can be applied. So it can be applied in several domains. So these are my current research activities. So we can apply them for optical flow, also for computational fluid dynamics, or also for control in model-based reinforcement learning. And also in quantum physics, where the use of simplified model can be also interesting. And certainly one open question nowadays on all the work I present in, I assume that you have that the derivative of your state vector can be linearly decomposed between a physical model and a complete and an augmented term. And certainly there remains room for improvement where this decomposition does not hold in more advanced complex application. Okay, so I won't detail that, but at the moment I have some application of this model for optical flow estimation. So I can give more detail if you are interested in the question session. So I think I will stop there. And here is a list of publication of resources with GitHub Cube if you are interested. So okay, thank you very much for your attention.
Thank you very much, Nicolas. It was very interesting work. So we'll move now to questions. So if anybody has a question, you can raise your hand or unmute yourself and talk to Nicolas. Maybe I will start. I have maybe a couple of questions. So when you were talking in your first part of the presentation, I don't really know if you use it, if you still use this notion in the second part in the affinity framework, but when you were talking and finding a latent space of your states or observations, how do you exactly do that? Yeah.
So in this model, you mean?
Mm-hmm. Yeah.
So here in this simple model, so this was the first idea that we had, and here in this simple model, there is no constraint at all on how the decomposition is performed. So here basically you have an encoder, so it projects your data into a latent space, and then you assume that your dynamics can be decomposed as a sum of these two terms. And then so you do not explicitly control what's the importance of this physical term coming from where you
so
inject.
Basically, you can have all of the dynamics in the convalescent part. And
yeah, you could. In practice, we did not observe that, but in theory you could, and that was really what has been motivating our subsequent work. Yeah.
Okay, so there is. Thank you, Nicolas, for your answer. So there is a question from Stephen Moreau in the chat. So he's asking whether what is the biggest advantage of the Pdenet over PDEnet? Is it that PDEnet assumes the physics to be explicitly known?
Yeah. So yes, certainly we can see two main differences compared to this PDEnet framework. So as you said, in PDEnet you assume that this linear PD is fulfilled or describe your dynamics well, and certainly this is an assumption that is not that does not all in all application. So this is one difference, and here. This approach, we try to combine this derivative coming from this Pdenet model with a data-driven component, a data-driven complement, and also we encode our data, so our inputs into a latent space. And so it was an application where we assume that we have a prior knowledge, but this prior knowledge cannot be expressed in the input space. For example, in several applications, this simple PD model it's not meaningful, or it's not useful to leverage that in the input space, or here in the space of pixels for video prediction, for example.
Thank you, Nicolas. Maybe another question regarding the affinity framework. So how do you do exactly the learning? So do you solve the PDE or no? You do not solve the PDE. You solve for the sum of derivatives, right?
Yeah. So yeah, it's really here. It's really based on the neural ODE framework.
Okay.
So you have your theta p and theta a parameter. You sum them, and as soon as you have summed them, then it's as it is done in the neural ODE framework.
You can just solve your equation using some ODE solver. So okay.
Yeah.
Do you use adaptive step size solvers or fixed step size ones?
Sorry.
Do you in the solve ODE ODE, do you use adaptive step size, or do you use
no, here it was simple. Okay. So we use a simple if I will remember, solver based on Runge-Kutta finite difference methods, but yeah.
So basically match trajectories. Thank you.
Yes, Said, Maxime, maybe another question. Yeah, you hear me?
Yeah.
Okay, all right. Thanks, Nicolas, for the talk. I have also one question maybe regarding what you said in the conclusion. So basically your decomposition relies on a linear decomposition between physical model, can be seen as a coarse version of your field, and a data-driven model for the small scales. And I was just wondering if you had some thoughts on how, in the end, maybe the small scales may interact with the coarse version, and how, yes, you can go beyond this linear decomposition, especially for physical models that we are working on in the team.
Yeah. So the short answer is not really, but it will be interesting to discuss with you guys. But in the experiment that we actually did, so the FA component is not really meant to apply at a different scale of at a different resolution level that the physical counterpart. But in many other applications, of course, it can be the case. And really, for example, in a computational fluid dynamics, one of our objective I'm working this topic in colleagues from computational fluid dynamics, and one objective is to really rely on solvers that solve the problem at a coarse level, and to try to use machine learning to make it work at a more fine-grained level. And here, of course, the main challenge is to properly write the equation and to understand how the augmented component should complement it, and how the multi-scale effect can be written in this context.
Okay, so thanks, Nicolas. I think maybe we have another question from Hugo in the chat.
Another question in the chat is actually pretty much linked to what you were discussing. Yeah, so Hugo asked about, so you basically answered it already, but he asked about how using, is it possible to use affinity to solve subgrade modeling problems such as large ED simulations. So basically, that's what you are trying to investigate.
Yeah.
Okay, so if there is no other questions, if there is no other questions, that's okay. There is other ones, you can ask them. But if there is no other ones, thanks again, our speaker. Thank you very much, Nicolas. It was a very interesting talk. And,
okay. Thank you very much for the invitation, and do not hesitate if you want to have more detail on these works.
Thank you, Luca. So, and see you hopefully in the next month with another session.